So I was making this video and got interrupted, so I'm just coming right back into it here. For this video, I want to talk about the second kind of calorimetry problem that you could run into, and that is when the heat that is given off of something that is hot and absorbed by something cold. So we're assuming all of the heat lost by whatever the hot thing is absorbed by whatever the cold thing is. They have equal magnitudes and opposite signs, and we're assuming no heat is lost to the surroundings. So what I had started working on here was kind of recreating that problem that we did in class, where I heated a nail in a Bunsen burner flame, got it really red hot, and had a beaker of water off to the side. We put the hot nail into the beaker of water. The temperature of the water did go up, but not by a crazy amount. And so I kind of want to go through this problem and look at why that didn't happen, why it just went up a little. So I am kind of assuming that the mass of the nail we used might have been around 2.2 grams. The nail is irons, and the specific heat of iron is 0.444 joules per gram degree C. We did figure out the T final of the nail because it became, it reached thermal equilibrium with the water. So we let the hot nail sit in the water until the water had heated up as much as it was going to. That meant that the nail and the water were at thermal equilibrium. So that's kind of all we know about the nail, and what we're going to be trying to figure out is how hot was that nail to begin with before we put it in the water. The mass of the water, we had 100 milliliters, so that's 100 grams of water. Specific heat of water, of course, is 4.184 joules per gram degree C. T initial of the water, let's say, was 25 degrees C. T final of the water, let's say, was 27.2 degrees C. Alrighty. So here's what we can measure. We can measure the amount of heat absorbed by the water. We've got enough information there to figure out how much heat was absorbed by the water. We're then going to assume that it came from the nail and work backwards to the nail. So we're going to have to do two separate Q equals MC delta T problems and flip the sign in the middle. So the heat absorbed by the water was 100 grams times 4.184 joules per gram degree C times the delta T. Remember, delta T is T final minus T initial. So 27.2 minus 25, that's 2.2 degrees C. Let me multiply that out. Do I have a calculator here? Okay. I left my phone at school, so I am really kind of doing this as best I can. Well, 100 times 4.184 is 418.4 times 2.2. And that is 920, well, I'm going to have two sig figs in the end. So I'm just going to go ahead and put that down as 920 joules. That's the amount of heat that was absorbed by the water. We are therefore assuming that the heat lost by the nail was that amount, but it was lost, so we're going to say negative 920 joules. Okay, now what I'm trying to solve with for the nail, excuse me, is its initial temperature. I could set up the algebra to go straight to initial temperature. I think that's harder than it needs to be and put you in a situation where you're more likely to have algebraic mistakes. So I am going to solve first for delta T. Delta T is Q over MC. So negative 920 divided by the mass of the nail we had said was 2.2 grams. And this is joules up here. And the specific heat of the nail is 0.444 joules per gram degree C. Okay, grams cancels, joules cancels. That degree C is going to pop up to the numerator. So I've got negative 920 divided by 2.2 divided by 0.444. And I get 942, so negative 940 degrees C. Okay, so, but that's not T initial. Delta T equals T final minus T initial. I've got to rearrange this algebraically to solve for T initial, of course. I'm going to add it over here. I'm going to subtract delta T from that side, and I'm going to get the T final for both the nail and the water was 27.2 degrees C minus negative 940 degrees C. So that, boop, 940, well, plus 27.2. So T initial was 967 degrees C. I think that's right. Okay, that's one of those something hot going to something cold problems. Another one that we saw in the free response we did in class last week had you doing a, I think you had, in one of the problems, you had figured out using a PivNert that 0.766 moles of CO2 was formed in a reaction, and that the delta H for that reaction was negative 1,270 kilojoules for 2 moles of CO2. If I remember correctly, that's going to be around 486. Let's see, 0.766 times negative 1270 divided by 2. Yeah, 46. So 486 kilojoules of heat was released. You were burning, I think, ethanol in an enclosed room, and that much heat was released. The follow-up question told you that all of the heat that was released by that reaction went into the air in the room. So the reaction is our thing that's hot. The and the thing that is cooler is the air that it was putting the heat into. So you had to assume the heat gained by the air was the opposite of the heat lost by the CO2, by the combustion reaction. So that meant that the air gained 486 kilojoules of heat. Okay, so I think they gave you an initial temperature of 21.7 degrees C for the air. They were asking for T final for the air. They had some really huge amount of air, like 500, it was 5 point something times 10 to the 4th. But what you had to do, you were trying to get T final. Again, I would not arrange this algebraically to solve for T final. You can, but you're just putting yourself, you're having to do more little, strokes on your calculator, more likelihood to make mistakes. Instead, I would have said the change in temperature, that's not heat, of the air would equal the heat absorbed over the mass times the specific heat. you would have had to put this 486 kilojoules into joules because, of course, the specific heat of air that they gave you was something like 1.005. I don't remember exactly the numbers, but I think everybody remembers doing this problem or not doing this problem because a lot of people looked at it and skipped it. But it was basically something hot is putting heat into something that is cooler. The something that is cooler here was the air. So the air gained the heat loss by the combustion reaction, and then we had to find the final temperature of the air. And then there is one more problem that I wanted to discuss briefly. If you've got the handout that I gave in class on Saturday, there was one problem that at first I told everybody in the room to do, and then I realized it was kind of an annoying problem, and I told them not to do it, that we didn't really have time to spend on that particular type of problem. But let me put it down here. And I'm not going